Cast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's webinar entitled Move Over Prototyping, Additive Production is Here, 5 Tips for a Successful Transition. I'm Jim Anderton, Director of Content for Manufacturing here at Engineering.com, and I'll be your host for what will be an interesting and informative hour. Now, we know metal additive technology delivers great ROI in prototyping applications, but what about production part making? Moving from a few prototypes to full-scale production, well, it's not a straightforward journey. Now, have you struggled with deciding where to start? AdWorks is GE Additive's in-house engineering consulting team, and they help companies with additive part development and production in the automotive, aviation, and energy industries. And today, Steve Slusher from AdWorks will share what he's learned from helping GE and other organizations adopt additive manufacturing for full-scale production. In today's webinar, Steve will discuss GE's approach to integrating design and manufacturing to print complicated assemblies, understanding and controlling the critical factors that impact variability, and definition of the post-processing required to ensure high-level part quality. Now, just a reminder that Steve will be answering questions at the end of his presentation. Just type your question at any time during the presentation into the console on your screen, and Steve will address as many as possible, and I'll host those questions. Now, about Steve. As executive leader at AdWorks, Steve Slusher has been with GE for 16 years with roles in design, testing, and certification. Now, he's led teams on several GE aviation commercial product lines. And since joining GE Additive a year and a half ago, Steve's established a multi-regional team to industrialize the existing laser and electron beam product line and the surrounding processes. The team has worked with both internal and external customers to help them advance their additive journey into piece part production. Steve?
Thanks, Jim. Good morning, good afternoon, and good evening to all those on the line. I appreciate your time. So for the next 45 minutes or so, I'm going to go through a presentation about GE and our additive journey and how we can help along the way. As Jim mentioned, my role is part of the GE Additive AdWorks team, specifically around helping our customers industrialize their products for serial production. Before we get started, I'd like to take a quick minute here and understand where the audience is and their additive journey. So Jim, I'd like to take a quick poll if we could.
Thanks, Steve, and we will. For viewers, the poll is on your screen right now, and the question is, which describes your organization's manufacturing capabilities? Please select one of those 3 answers right now. Either use conventional manufacturing and CNC technology only, have integrated some metal additive manufacturing technology, or we outsource the printing of some metal 3D parts. And we have poll results coming in right now. Go ahead and select one of the 3 on your screen to answer the question, which describes your organization's manufacturing capabilities. And we're collecting responses in real time right now. Your choices are use conventional manufacturing and CNC technology only, have integrated some metal additive manufacturing technologies, or we outsource the printing of some metal 3D parts. And results are still coming in real time. We see them coming on the screen right now. We have about another 55 seconds to go, at which point we'll reveal the poll results, which describes your organization's manufacturing capabilities. Voting coming in now, or almost complete. And here are results. Steve, it looks like 48%, or the majority, have integrated some metal additive manufacturing technology, as opposed to conventional manufacturing CNC only at 28%. Are these results in line with your expectations?
Yeah, so as I talk to customers we realize that people are starting their additive journey. We think the majority of the people out there are playing with additive, whether it's design or prototyping. So this is really in line with what I expect to see.
Okay, it's great. And Steve, on with the presentation.
Okay, so to start off, a little bit about some of the customer feedback. I've been to several shows, been to a lot of our customers, and when I ask them about their barriers to entry into additive, there's 5 main recurring themes that come up. One is part identification, the return investment on their profit. A big one that is really out there is the experience gap from the transition from prototyping into production, overall talent resource shortage, and then the cultural resistance to change. So when we think about the experience gap, that's throughout the entire organization, not just the traditional engineering experience gap that one might think of, but you got to think of supply chain, sourcing, quality, manufacturing. All of those departments have to come together throughout the entire organization to help transition from traditional manufacturing into additive. Over the next couple of slides, I'm going to talk a little bit about the success stories that we've had at GE, and then go into what I would say the rest of the story, or the backstory behind them. So many have heard about the GE fuel tip. This is our main part that came into FAA certified production in 2014. Recently, as last month, we've announced that we've shipped now 30 of these fuel tips into production, 30,000 of these fuel tips into production. The benefit we saw was not just relative to cost, but from an inventory perspective, a 95% inventory reduction, a 30% cost reduction, and from an overall productivity improvement of 2.5x. So for those that do not know about this fuel tip, it's actually the top of this part, not the stem that you see for the entire part. The fuel tip was previously made of 20 different components that were all individually manufactured and brazed together. We now produce that as one complete piece and print about 600 of these parts a week. As we started this journey with the fuel tip and looked at process parameters and machine capability, we faced a challenge of how to incorporate this part on 175 machines to reach full rate manufacturing production. Through some of what I'm going to talk to you about today, we've minimized that down to just over 50 machines in the last 3 years, and have a path to get down less than 30 machines. Beyond just the laser powder bed system, we've also been practicing on the electron beam machines as part of our RCAM acquisition. So for the GE 9X, which is now in development and will go into production within the next year and a half, we're producing 2 sets of blades through our EBM technology. 6 blades are printed per machine. This is a titanium aluminide alloy. This benefit included cycle time as well as a 50% weight reduction. So now to kind of talk about the rest of the story a little bit. You often hear about the success stories, and we don't necessarily hear about all of the challenges to get there. And that's what I'm really here to talk about today. So for those of you that are maybe runners on the phone, I compare this to trying to run a marathon. You don't get up in the morning, decide to head to the starting line and run a marathon, right? You have to first take the initial step of getting out of bed at 5 a.m. to start your long runs. Along that journey, preparing for a marathon, you'll come across challenges, whether it's a knee injury, an ankle injury. Well, Additive is no different. As you go, you have to take the first step, which is getting your organization aligned, that you have a plan, a path, and a reason to go into Additive. Along that journey, you're going to face issues around build stops, build failures, machine-to-machine variation, build variation, which will really impact the enthusiasm a potential team would have to try to get into production. So just as we went through our fuel nozzle and brought that into production, we had non-conformances, we had variation, we had very intricate designs that we had to go and produce. We weren't hitting the productivity we needed. It wasn't until a few breakthroughs that I'll go through here today that we found a way to consistently produce that fuel tip into production. To the point of today, we're at a 95% yield on that fuel tip. So as part of our AdWorks team, our goal is to take this journey and eliminate that trough. eliminate all those production challenges to help you get from the excitement of a part that's been identified, you've done initial prototyping, and how do we get you to production without going through all the hardships and all the learnings that we've come across. The good news of that story is, just like after you run a marathon, the second one, you can take all of those learnings and implement those. We're doing the same thing within GE and across GE businesses. So here's a couple examples of how we've leveraged what we've learned on our field tip into GE transportation, for example, where it's not necessarily a cost benefit, but it's reduced cycle time and really to meet the new end user requirements. So for GE transportation, we're in the process of trialing over 250 additive components to bring into production in 2025. Within GE Aviation, we've recently certified on our Concept Laser M2 a bracket for the GE NX jet engine, which powers the Boeing 747s. In order to do this and move fast, we actually decided to take the part itself and do minimal changes to the part from the traditional part geometry. But we did change the material over to something that we already had qualified within the FAA, and that's our cobalt chrome alloy. So I'll take a second here and jump into maybe another poll question around, for the audience, around how they've invested into metal additive manufacturing so far.
Thanks, Steve. The poll question is on your screen right now. The question is, if you have invested in metal additive manufacturing, where are you on the path to production? Go ahead and choose one of the 5 options on the screen in front of you. Only exploring, no capital investment made yet. Learning how to build parts, making successful parts and prototypes, small scale production, or production volume. A poll question, choose one on the screen right now to answer the question. If you've invested in metal additive manufacturing, where are you on the path to production? And results are coming in right now. Please choose one of the following: only exploring, no capital investment made yet, learning how to build parts, making successful parts and prototypes, small scale production, or production volume. And results are coming in. Considerable results are coming in. In fact, this should be interesting. The question is, if you've invested in metal additive manufacturing, where are you on the path to production? About 1 minute in, and results are just about here. And here we are. Results. Interesting. For bimodal distribution here, 36% only exploring, no capital investment made yet, but a strong 34% are actually making successful parts and prototypes right now, and fully 11% are doing production volumes. So Steve, what's your opinion of that result?
So a little surprising. I think where we see a lot of people playing is in that we're making successful parts, we're building prototypes. How do I get into production? So it's encouraging that we have 11% of the folks on the line here in production volume. So that's a great thing. And hopefully, as I go through the rest of this around the production side, we'll have some similarities on that path to production that we found out along the way.
That's great. Thanks, Steve.
Okay, so let's continue on. Okay, so here's what we've learned, right? So the typical challenges as we go into production, there are 3 main challenges: printing repeatability, the part quality, and the manufacturing productivity. And I'm going to talk all three of these in detail. But as you think about printing repeatability, so this is things like site-to-site variation, machine-to-machine variation, variation across the build plates. So as we went through our field tip, for example, right, we have a multi-site qualification that we had to go through, a multiple machine qualification we had to go through. So as you think about that, you've got to look at all those critical X's that come across and how they interact between sites, between machines, to make sure that we understand them and control them. It kind of falls into the second one here, which is around part quality. So part quality starts with powder, how you handle powder, how you spec your powder from your vendors, how you look at your powder reuse. Also comes into play of your build-to-build variation, and something to think about that traditional manufacturers don't necessarily have to think about is the benefit of additive is the unique features that you can put into these parts, the complex geometries, which often yields challenges on quality and quality inspection. And the third is the manufacturing productivity. Just like any business, productivity is key, always being challenged to go faster, do more, get more productive machines. So you have to balance this with the first two. How do you make sure that you're getting the right amount of speed with the right amount of quality, and making sure that your entire process is repeatable, no matter if you're making a part here in Cincinnati or in Auburn like we do on the field tip. The reason I think these are the main challenges that people see when they go into production, because as you think of a prototype, building one part on one machine, a lot of this doesn't come into play. Yeah, you want to take a look at your printing repeatability from build to build, but you don't necessarily have to be concerned around multiple locations or multiple machines or multiple vintages of machines. So I talk about repeatability. I hit on this a little bit, but the key factors that come into variation, not understanding what those critical X's are, right? Whether that's the power settings you're using in your parameter, your scan speed, your oxygen level of in your build chamber, the spot size you decide to use. Those are just a few of the critical X's, and those critical X's are really focused around the machine. There's other critical X's around powder chemistry, powder handling, and post-processing that need to come into play as well. So not only identifying those critical X's is important, but also understanding the ranges of control. My power, for example, can I vary to 10 plus or minus 10%? Can I vary plus or minus 12%, 15%? What's the right number? When you think about airflow, right? Airflow is highly important in the additive process. What type of variation can I withstand across the entire build plate? What variation can I withstand between machine A and machine B to make sure I'm getting the equivalent material properties? The third one, which people I don't really think they think about as they go from one machine to the 50 machines over the course of, say, 3 or 4 years, is the technology is rapidly changing, right? So a machine I order today may not be the same machine I order in 3 years. Right? So how do you understand the machine configurations and understand its impact on your process and on your part? One way to do that is to lock down that machine configuration going forward. And the last piece here is the work instructions for operations and maintenance. So think about your operators on the floor, right? They're all trained, hopefully with the same training process, but each of them takes away a little bit something different. Having complete work instructions that are followed allows you two things: to ensure that, one, the process of producing the part was the same, but it also helps you diagnose any issues that come across. As we went through the development and production process, we often find a build failure and try to go back and document what exactly happened. And without complete work instructions that were followed, it makes that very difficult. Moreover, on the maintenance side, think about your preventive maintenance schedule. How often do I have to validate machine calibration, for example? How often do I have to recalibrate my oxygen level sensors or check my airflow within the machine? How often do I have to change my filters out? Those are all things that are part of that industrialized process that need to be documented, maintained, and controlled. When you think about multiple sites, or even looking at service providers, right, there can be variation in all of these, right? So one of the things GE Additive announced was our manufacturing partner network, right? The goal behind that is to help minimize this type of variation, to make sure that when you go to one of these service providers that has been authorized by GE Additive, the expectation is that we get consistent results. Part quality, it starts with a quality control plan, right? So the first step is really tying off between engineering and manufacturing and quality, so that your quality organization, which may not be accustomed to the additive process or additive manufacturing, understands what the design intent is, understands how the manufacturing team is going and developing the part in order to meet those design intent. So the first thing here is an overall control plan. Right? How often, what are your actual tolerances that you need to, how often you need to measure, what kind of tolerances you need to withhold, and how many parts you need to go inspect. So step 2 around this is that inspection plan and techniques. As I mentioned earlier, the additive process, additive design is absolutely great for unlocking the engineering innovation, but with that comes very unique geometries that differ from the traditional perspective. So how do we inspect those? Whether that's white light, CMM, CT. How do I inspect the part to make sure that I have complete powder evacuation from internal cavities? All things that are critical to getting part quality from a geometrical and a metallurgical perspective. The third one here, the metal powder handling procedures, is something I think a lot of folks in the traditional manufacturing aren't necessarily accustomed to. So in this environment, powder can be reused, recycled, but it has to be controlled. We have lots of powder, which is similar to the traditional, but as that goes through the process and produces parts, you have a lot of powder that is able to be recycled, reused. So how do you validate how often you can reuse that powder? How do you validate your handling procedures, your storage procedures? This also has to have a strong tie to EHS and safety. And then the last bullet around continued process validation. So you're continuously learning as you go. Right? There's going to be new technologies that come out relative to powder handling, relative to inspection. What's the ongoing equipment validation and part builds you need to do to ensure you have a stabilized process? Right? This is all part of what we would consider our machine qualification process. And then the last piece around the challenges is the manufacturing productivity. So I hear a lot from our customers that, let's say, I've got a part and I currently pay X amount for it. Additive is too expensive because if I look at how long it takes me to print, it costs me Y. I need your machine to be 2x more productive than it is today. So one of the key takeaways that we've learned is we can increase the productivity of the machine. We can go from a single laser to a dual laser to a quad laser system, right? But we got to understand those trade-offs. So going from a single laser system to a dual laser system doesn't necessarily mean we have a 2x productivity and speed. You also got to take into account things like your tool path, your recoding time, making sure you don't have laser-to-laser interaction. So I think about capturing the overall productivity. It includes things that are outside of the machine. How do I increase laser on time, for example, on the machine? If it takes you 2 to 4 hours to switch over a build, how do I take that down to 15 to 30 minutes to gain productivity? How do I look at my post-processing? What's my HIP process look like? What's my heat treat process look like? So I want to make sure people understand that when you look for productivity, you're looking at the entire process, not just the machine itself. Parameter development is another area that can have a huge impact on the productivity of the machine, whether you're printing at 25 microns or 50 microns. The other one I'll touch on here is really the last bullet, the build platform and part supports. Are they designed for production? So when you go into prototyping, I can over-design my part supports. When you go into production, you really have the opportunity to optimize those, whether that's varying my layer thickness or whether that's optimizing for downstream efficiency. So for example, on the fuel tip, as we went through the ramp up from producing on 5 machines to now producing on 50 machines, we noticed that during the build support removal process, there was a lot of manual touch time. We had operators breaking away supports. So we went and developed a robotic cell that allows us to now automatically remove some of those supports to decrease operator time and increase our EHS capability and standards. So now for a couple tips that we've learned along the way. So we think about and work with our designers on the actual design of a component. We got to look at it not from the traditional method and not even from the 3D method, but it's really from an additive production perspective. And that comes all the way down to powder removal, support structures, right? Those type of things all play into the production capability and production productivity of a part. So if your support structure is dense and elaborate, right, you can actually slow down the process very significantly, and it can become a manually intensive operation to remove those supports. If you can go and design those supports that they could break away quickly or with some automation, those are all things that will help you in the process. The second piece of this is something that we struggled with, right? And as we've become more intelligent around AM and the market has increased as well around us, it's determining your vertical integration strategy and the impact on productivity. So it's balancing the two, right? So in the graph here, this is really notional, and it's for each individual company and organization to decide on. But if you balance technology and complexity, and as you get up to the top right corner, that's where we see the most value. Right? The things in the bottom left where you'd say, it's not complex, that doesn't have a lot of technology involved in it, things like traditional machining or turning of parts, some of that post-processing, right? Those may be areas where you as an organization may want to outsource those type of things and vertically integrate the things that are going to be of the most value, which includes both from the cost perspective, the productivity perspective, and obviously the intellectual property perspective. So I challenge you to think about that for your organization and make sure your entire organization is aligned to that strategy. So the third piece is identifying your critical X's and the tolerance ranges around them. So I talked a lot about this, right? There are hundreds, if not thousands, of different variables in the additive manufacturing process. All the way from the back to the powder vendor in how they create the powder to the quality inspections and quality inspection techniques. The biggest hurdle we see here going from prototyping into production is evaluating each of those critical X's can be a daunting task. So developing ways to quickly understand the influences of all the X's and which ones are the most critical to your process, to your part, to your material requirements is paramount. 4 is really employing the statistical quality control. So when we go in regulated industries, this is all about showing reliability and repeatability to the regulators. How are we looking at machine to machine variation? How are you monitoring those critical X's, and at what rate are you monitoring those critical X's to show that a part coming off a machine in one location is equivalent to a part coming off a machine in another location? And the last one here, the knowledge transfer process and cross-training is absolutely important. So when we think about what made us successful, if I would have designed a fuel tip in a vacuum, had my designers in a different building, not working directly with my manufacturing engineers, my quality engineers, to really understand and bound the additive manufacturing process, it could have taken us several more years to get through the lead fuel tip. But what we've come to realize is that having those 3 functions co-located to focus on the product that we're trying to produce, to understand the trade-offs between design, manufacturing, and quality, helps you both from a cycle time perspective, but as well as making sure we have the best product and most well-balanced product out there. So this brings us back to why I exist, why GE Additive AdWorks organization exists. So as I said at the very beginning, we talked to a lot of customers, a lot of different shows, a lot of different events. And I think we came to realize that the need for an organization to walk hand in hand with our customers through their additive journey was absolutely important for us to be successful and to accelerate additive within the entire industry. So we help along the way to help develop the business cases, understanding of the effect of supply chain, not just from the piece part cost, but from the overall business costs. From the design perspective, again, not just the piece part design, but also from a design for additive manufacturing. We've got capabilities in-house to go make parts from a prototyping perspective, from a low-rate initial production perspective, and more importantly, to help you along your journey to get from that prototype phase into that production, whether that's with a supplier or internal to your own organization. And then the qualifying process, whether that's a regulated industry or not, the quality requirements from an automotive perspective or from an aircraft engine perspective, we understand those and can work with you to make sure that the processes are in place to make sure you have the right quality. So today within our AdWorks organization, we have resources around the globe that are available to go and work with you wherever you're at in the journey to help you get into production quicker. So I put my contact information on here. You're free to reach out to me individually via email, via LinkedIn or any other social media. But for today, I think that's all I have. I would like to turn it over back to Jim and walk through any questions that the audience may have.
Thanks, Steve. And we have multiple questions from the field and some interesting questions here. Several of them relate to powder, to material. Can you comment on the material issue, both in the availability of different metal powders, but also that powder is optimized for specific applications. Of course, the gas turbine engine one is the prominent one. What about other applications and powder availability?
So, for those that don't know, we also, as part of GE Additive, we have AP&C, which is our powder manufacturer, but we also offer a wide range of powders. So you'll see powders that are in the Inconel family, so the 625, 718s, the stainless powders from the steel perspective, the 316s, Mar-aging steels, the 350s. We are able to print in things like aluminum, which is the aluminum silicon 10 mag F357 type of materials. Obviously, our cobalt chrome materials. Titanium is another one that we use. So we think about it, a lot of what GE has started with was materials that are focused on the aviation environment because that's where we've traditionally played. But recently we've expanded that to get into more of the medical as well as I would say the automotive industries with aluminums and steels, especially things like the tool steels as well.
So clearly, we're talking about higher value materials here. These are we're not going to be working with commodity carbon steels.
Correct.
Yeah, that makes sense. Now, the fuel nozzle, of course, for the 9X engine, of course, that's the original, the big win. There's a lot of jet engine sort of high value part making going on here, and you mentioned FAA certification for shops that are working in a certification environment like that. Could be aerospace, could be healthcare at this point. Is the certification process different for an additively manufactured part compared to a machined part?
So, outstanding question. So, the certification process itself, right? When you go to the FAA or EASA, it's fundamentally the same, right? It's whoever the type certificate holder, it's on them to show that the part meets the data that you've collected, right? So at the end of the day, whether it's an additive part or whether it's a subtractive part, you've got to go to the FAA and you've got to talk to them about how you demonstrated the part meets the design requirements, the design intent, both from a geometry perspective and a mechanical property perspective. So from that broad scope, it's equivalent. But the how you go and demonstrate that to the FAA is where additive differs a little bit. Okay? So today there's a lot of understanding around traditional manufacturing, forgings, castings, and billets. When you think of additive manufacturing, you've got that entire foundry and the manufacturing finished product all happening in one spot, right, within a machine, along with the post-processing, right? But it's how you understand and take the critical X's that you've defined and prove to the FAA that you understand the process and the parts are meeting the material capability that you've demonstrated through whatever material test program you have. So that's where a little bit of the challenge comes in.
Yeah, Steve, many conventional processes, of course, involve things like die casting, investment casting, and then post casting machining processes from snagging castings to finished machining. And those are well characterized, well understood processes down here. The assumption always has been to switch to additive is that you then redesign the part to exploit the advantages of additive. But if for reasons that you can't do that, you're locked into a certain design, can you still make a case for making the switch to additive manufacturing from conventional machining processes?
Yeah, so I talked about earlier today, our bracket that we just put on we just got certified to go on the GE9 or GE-NX engine, which is already certified. That was an existing part that was traditionally manufactured. We made very minimal changes to it, although we did take a chance and look at, from a geometry perspective, we made small changes, but from a material perspective, we did change that material from an Inconel to a cobalt chrome. And we didn't necessarily need to go do that, but the reason for that is because we already had cobalt chrome certified through the FAA. So we already had that entire data set. But those opportunities are rare, where you can take a traditional manufactured part and do a one-for-one swap and expect it to be fully cost competitive. Where I think if you want to go and try to look for items where it's a direct one-for-one swap, that typically is because you have a lot of hidden cost in the part. Meaning, I've got a supplier that is struggling and I'm paying for expedited fees, or I'm having quality issues and we don't have a good yield from a part perspective. So those are other areas where if you look beyond just part cost to part costs and look for those hidden costs, where additive really comes through from a one-to-one part swap perspective. As I mentioned in the past, the real power of additive is redesigning a system around additive and additive manufacturing.
Steve, there are several ways to skin a cat in additive. Multiple technologies and new ones are arriving all the time. In terms of sintering from powder beds, a couple of popular ones are electron beams and laser. Does it make a difference how you melt that powder?
Absolutely. So every technology, so laser powder bed may not be the technology that is optimal for every component, even if that component can be printed additively. And I say that because if you look at laser powder bed versus EBM or things that are coming down the pipeline from GE Additive like binder jet, three distinct technologies, and each has its own area where it can play in component manufacturing. So you look at EBM, for example, it's a faster process than laser, but it'll give you a rougher surface finish. Powder removal is a challenge, so tight cavities, tight bends are something that you want to stay away from the EBM side. Laser, I can get finer feature fidelity. I can get powder out of internal cavities a lot easier, but it's a little bit slower. I can't stack parts like I can on the EBM to take full advantage of your Z height. And then you get into things like binder jet, right, which are really around productivity. Right, it's a step change in the productivity perspective, and offers you, I'd say, more low cost opportunities. So absolutely, depending on which way you go in additive, is going to give you different part capability from a geometrical perspective, and your overall processing may be different. Right? If I go through EBM, my post-processing is going to be different from a heat treat perspective than it would be on a laser, for example.
So speaking of heat treating, do you post-treat heat treat additive parts the same way you do machine parts?
So the one thing from a post-processing, and right, this all comes down to individuals' applications and their organizational requirements. So today within GE, we hip our parts, for example. So that hipping process is all around increasing the density, reducing porosity in the part. So we go through that process for all of our parts. That's not necessarily saying that you have to in every industry. It all depends on what material requirements you need to go through. But from a heat treat perspective, GE and GE Additive have an organization full of material application engineers that look at our customers' application and application requirements, and we can develop heat treats to make sure we get the properties they need to meet their design requirements.
Yeah. Yeah. Steve, in terms of design, one advantage of this technology, of course, is that you can design topologies or use topologies that would be absolutely impossible to consider in any other form of manufacturing. But how do you optimize the design topology? That's something which you can do just with essentially inspiration, creativity. I mean, do you recommend going to software to do that? I mean, how do you get to the best possible shape?
So that's a great question. So as you look at some of the parts that are coming out in additive, you can see that they're almost organic looking, right? So the way I talk to our customers when we have full reign from a new design perspective is understanding the requirements. So first step, what interfaces do I need to maintain? What structural integrity do I need if I have to have gas flow through the part? Do I have liquid through the part? Right? Making sure you understand those. And then, this is where the unique capability and I'd say creativity of our design team comes in. So the design team here, we've actually had training where we go off-site and really try to keep their minds sharp and fresh around being creative with designs and features to make sure we meet design intent. So no more sharp-cornered edges when we're talking about flow areas, right? How do we make sure through CFD that we are getting the most optimal design to allow for flow, so that we have laminar flow, less turbulent flow through a system. So today, I think my answer to that is imagination is key, but understanding the principles of manufacturing, meaning I can't go and have overhangs that are unsupported over a certain angle, right? Making sure we understand those to bound the team a little bit is important, but allowing the team to focus on part requirements is key.
Yeah. Steve, you made a comment earlier slide, the machine must be locked down for production configuration. In subtractive techniques, of course, you do that simply by, in the machining example, for example, you've got your G code. Your G code basically is tested, maybe simulated. Its revisions are tracked, but it's fairly easy to put that into a PLC and then close it off for further access and control it that way. Get a real revision control system going. Does it work the same way with additive?
Not quite. So this is where, when you think of a CNC process or a traditional manufacturing process, we don't classify those as processes that are special processes that require what we do here, which is having certain sign-offs from experts to say that those processes may change fundamentally change the material capability. So when you think about, I got to lock down a process in a traditional manufacturing, it goes speeds, feeds, etc. You can lock down process parameters on a machine, which is great, but you also got to look at the entire machine and how it can contribute to variation. So today, if I make a change on my machine that takes my nominal gas flow, for example, and improves it 20 or 30%, as a machine manufacturer, when I deliver that to a customer, they need to understand how it impacts their process and their part. So think about that from the foundry perspective, right? I may be, by changing an airflow characteristic, impacting the material properties of a part. Whereas in a traditional, I'd say, CNC or lathe operation, changing my speeds and feeds doesn't necessarily mean that I'm going to change the fundamental metallurgical properties of my part.
Yeah, that makes sense. So, Steve, you talked to a lot of people in this business, and we have seen from the earlier poll a surprising number of attendees out there are using this technology for prototyping. But what's your biggest surprise when you talk to customers who are building prototypes today, but then want to make that move to production?
So it was a great question. I had this conversation yesterday, actually, with someone, with one of our customers, and the decision when you go from prototyping into production is two things. One is, what am I going to do? What am I going to outsource? So today, where I think people are at, I get surprised when people are putting prototypes and they don't necessarily have an understanding of, I would say, repeatability and reliability drivers. So I mentioned earlier in the presentation around going from 1 machine to 50 machines, understanding the things that drive variation from machine to machine or part to part or build to build are absolutely critical. And one of the things we talked about with this individual yesterday was the capacity in the marketplace versus the capability in the marketplace. So there's a number of machines out there. People have 1 to 10 machines, but there's only a few people that have 10 or more machines out there that are really driving to understand the repeatability and the reliability of these machines and the overall process. So I think that's the biggest surprise I get from people when I start talking to them about and asking them about how they're demonstrating repeatability or reliability. And that's one of the biggest hurdles to overcome from this prototyping into production. Jim?
Steve, yeah, another question on the floor is rather specific. Is it possible, do you see a future role where we can take machined or pre-existing parts and use additive processes to build onto them?
Absolutely. So the challenge behind that today is twofold. One, around making sure we understand existing parts and their location in space, right? So the accuracy to determine where exactly you need to build. And then material compatibility is the other one, making sure we have the materials available that can help you build upon existing materials. Just like you would do in welding, right? You got to make sure you have compatible materials to have an efficient and effective weld. So I see that coming down the pipeline right now, and we have things going on from the additive manufacturing world around DED and other technologies that are starting to go that way. I think this isn't a far putt for us to go do within a laser powder bed system.
Steve, in this attractive world, the labor shortage is a serious issue for American manufacturing. And of course, one way they're addressing that is to go with automation. A lot of machine tending and more advanced functions as well. But will we see that same tendency, you think, with additive processes?
Yeah, so absolutely. I think as I talked about productivity will drive it. Right? So an entire process productivity, whether that's removing powder from a build chamber more efficiently, more effectively, whether that's taking a part out of a build chamber, removing supports, removing it from a build plate. I think automation is definitely where the industry is going. You look at GE Additive and our M-line product that we're coming out with. It is the first step in that serial production automation realm, where the part now gets built. It'll move to a processing or handling station to have all the powder removed automatically, to reduce both touch time from operators as well as the EHS concerns as well. So between the shortage of, I would say, experienced operators as well as the EHS concerns around additive manufacturing, I think those two will drive the entire industry to more automation.
Yeah. And Steve, related to the automation question, for validating the build, of course, in the CNC world now, the tendency is to go to simulation to avoid having to go and basically occupy very expensive machine time, test cutting physical parts. Is the same thing true in additive?
So for validating builds, there's different ways to go do that. Some customers and processes that we do, we validate builds by adding test bars onto the build plate. And they can quickly cut those and look at porosity, look at tensile capability. Where we want to go to as an organization, as a business, our concept laser products have a QM melt pool system, which allows you to actually look at the melt pool as you're printing a part. So where I see this heading in not too distant future actually is utilizing that melt pool to validate that your build is acceptable. So if you can think about every layer, you validate that you've printed the same way you've printed 10,000 times before. Right? That's one, so you know you're going to get the same densities, the same fatigue capability of that part as you did on the previous 10,000. That's a different way and a more productive way for validating these builds. And like I said, I don't see that. I see that coming around pretty quickly as we go to production.
Yeah. Speaking of production, Steve, GE is a little unique in that you actually make and develop additive manufacturing processes, which are also a major consumer of additive manufactured parts. Was there a breakthrough moment that you had when you went from this technology and actually decided to go ahead and make production parts with this? We're talking about jet engines here. It's a safety critical application.
Yeah, so I'll tell you, the aha moment to go and say we are going to go additive production. So the fuel tip that I talked about earlier and most people are aware of here is for our LEAP program. And as we started going into the design, anybody that's familiar with jet engines and our friends at Boeing and Airbus, there's constant pressure to have higher reliability, higher durability, and oh, by the way, we want better SFC, specific fuel consumption. So we were constantly challenged, right? And as we started designing and developing this fuel tip, it became very apparent that in order to get the gains that we needed, traditional manufacturing just wasn't an option. We couldn't get the repeatability, the reliability of a traditional manufacturing process, which included brazing, et cetera, to get us to a yield that we needed to hit the production rates of the LEAP engine. For those that don't know, the LEAP engine is our highest selling engine. We produce at full rate about 40,000 fuel tips per year. So at that moment, it became very apparent that additive was the only way we could go. So that's where we went through and combined the 20 parts into one. And then I'll say another aha as we went through that process, because that's where we said, okay, we outsourced that to a facility down the road here, Morris Technologies, which we eventually acquired. They were able to produce that part. But then to go to production, I think our aha here was in the development facility when we started making that part at 5, 10 machines, we quickly realized the machines needed help. We needed to have more reliable, repeatable machines. And so we started pushing that technology in order to help us get to that production state. And so that's where you see how GE Additives now come about, which is, we decided to go and take those machines and all that machine learning and putting it into our own machines that we can go develop and make sure that we continue to push the technology envelope and the capability of these machines to make more complex geometries and hardware for us going forward.
And Steve, with that answer, we bumped up against our hard stop at the top of the hour. I know there are many questions to answer, and it's great of you to put a slide up there giving access, direct access by email for folks who have further questions for you. I'd like to thank General Electric for sponsoring today's webinar, and I'd like to remind also all attendees that this and all engineering.com webinars will be available online at www.engineering.com for later viewing. Thanks, everyone.
Thanks, Jim.